Okay, hello everybody. This is going to be our last, our fourth and last video on working with R. So I'm going to cover some more advanced kind of tricks of the trade here. Before I kind of go into these, let me sort of give you an overview of what I'm going to do. First, I want to kind of talk about control structures or loops in R, and then also conditionals, and then I want to talk sort of about the various arguments that different tests use. I'm going to be showing you a script that's in your kind of example code called MyR plots, and it has some features there that I want to talk about. The first is kind of extending the ggplot phrases to include themes and to allow for a lot more sort of control over the way your plots look. And then I want to talk also about doing multi-panel plots. That's putting more than one plot on your PDF, which is often handy if you're doing, more than one analysis or more than one thing, and you want to sort of combine them all into one nice visual. It's nice to be able to put anywhere from 2 to 6 on a single page. So I'm going to show you a package called Grid Extra, which lets you control the layouts of the ggplotting functions. Then I want to kind of finish up then by talking about controlling R from other languages, namely Python, and then also working from a language called Perl using a pipe, which is very handy if you're doing sort of automated tasks over and over again. So let's get started. I have a real simple script here that I found online, just kind of demonstrating a for loop. So this is the RStudio. This is the script up here, and on my console I haven't run that yet. So if I click source on save, as we talked about before, and I run that, you can see that it runs through this loop. It counts up the number of objects in my vector here, the number of values in my vector named x, and then prints out that number at the end. So that's fairly simple. Just remember that in R, there's really no white space or indexing like you need to do in Python. Code blocks occur in between these curly braces, and you can I believe you can set those up really any way you want. Typically, you're going to want to indent to make your code a little more readable, and do something like that. So if I were to add, say, a little more to this, if I'm within the loop, if you're ever debugging things within loops, you might want to do print statements within the loop just to see sort of what's happening. So if I print my values here and resave that, I should see there everything's sort of being printed. So I can actually watch as I'm walking down that vector. I can see each value. And then I might want to do something a little fancier. Here's a conditional. Let's say, just for the heck of it, if we only want to print, let's say, if my value is greater than or equal to 4. Actually, let's just say if my count is greater than or equal to 4. And we run that, and you can see it starts printing up at number 9 here instead. So technically you probably would want to use curly braces here it doesn't appear that R needs them. I'm just checking to see if this would actually still run. It does the same thing. So, at this point, using curly braces within curly braces looks like that's acceptable as a, so you could have a code block within a code block, or you can simply just ignore that. I think it looks a little better with them. If I were not within that code block and I was doing the conditional outside of these curly braces, I would then need to have them here. So that's looping. Let's talk a little bit about, before I go in and sort of talk about this more complicated script, let's talk about one more thing that you might need to be doing. A lot of times when we run R, we're really only running on one of the available cores on our computer. So again, if I'm in Linux and I just pull up something like HTOP, if you're in Windows you can pull up the task manager and sort of do the same thing here, but you can see that right now in this laptop I have 8 cores that are available to me here to be doing computing on. So I could be doing 8 tasks in parallel if I wanted to, and that could be handy, especially if I'm doing something with machine learning or something that might be sort of intensive, especially if I'm going to take my R script to, say, a supercomputing grid. I might have hundreds or even thousands of nodes that I could run something on. So knowing how to do that is a little beyond the level of this course, but I'll show you kind of where to start with that in R. And if any of you get into it, I do have examples of this process in some software that we've developed in my lab. So what I would point you to online is to look into, if you're interested in doing multi-threaded R or essentially parallel computing in R across your cores, you're going to want to use the for each package, and then another package called DoParallel. So DoParallel is essentially a parallel backend that works on the for each package. So these would be 2 packages you would need to install, and then in your code you would need to say library DoParallel and library for each. And then I'll put this up in up on the course as supplemental reading, and if any of you want to get into this, you can see here sort of how this works. So once you import the DoParallel library, you can use register DoParallel, and that'll actually register the number of cores that you want to use. And then an example code would look fairly similar to the kind of loop structure that I showed you before, but you would be using the for each command. So I'll put this up online for any of you that sort of want to sort of read through how to get started with this. It's really not hard to do. I use it in some of the R scripts that I've written for a coding project that I have. So I'm going to sort of show this more towards the end, because if you're interested, you can go to proteindynamics.net, which is the website where we have some of this software, and we run machine learning on however many threads are available on a given machine. So I can show you that sort of code if any of you are interested. So let's go back to RStudio and look at a more complicated script. So this is a script that I'm giving you in our sort of example scripts. So there's a folder on my courses that is called MyR Script, and in MyR Script I have lots of examples here. The data sets that this is analyzing are there as well. And you don't have to worry about sort of what deflux is. It's kind of a computational chemistry script that we were using and needed to do some plotting on for a paper. So the first thing you're going to want to need to do is read in my global and local flux values as data G and data L. So these are being read in, and I already talked about the read table function. Again, you're going to need to write the full path to like wherever your file is on your computer. If you're in Linux and you sort of are wondering how to do that, the command is always just pwd, path to working directory, and that'll always show you kind of where you are. You can do similar things at the Windows command line as well. Windows is a little less sensitive to having exact paths. So a lot of times it'll just assume if you're running it within the same folder, it'll assume that it needs to run only in that folder. So you could get away in a Windows script with actually just giving the name of the text file and leaving the path out. Again, my header is true because I have headers in those files, and the names of those headers are shown here. So in that file, if you were to, it's a tab delimited text file, and there's a column for my deflux, and there's another column called type in each of those two files. So here I'm basically assigning a variable name to that data, and then I'm also going back and building a data frame. Now you can work with, in R, you can work with data in the form of vectors, you can work with it in the form of matrices, and you can also work with it in the form of data frames. And it's often very useful and very important when you get into certain arguments of certain tests. They may require it to be a data frame and not a matrix, or they may require it to be a formula that involves vectors and not say a matrix or something like that. So you need to sort of, again, pay attention to what the arguments of the different tests are wanting. And I'm doing two tests here, and both of these have different arguments that I'll show you on the R documentation, different ways of writing it. And when we're in R, this is one of the biggest problems the students run into as to why their code won't run. It's often because, again, not because they don't, you don't know, it's not that you don't know what you're doing or that you're not writing bad code. It's often just that these particular functions have arguments that are often just different, and they require, and they're written by different people, so they don't always follow the same conventions. So we often just have to go back and be careful about that function and look up, how the arguments are supposed to be passed into that function. So if you have a matrix and you need to create a data frame, in this case I'm just taking my my vectors here that I've imported from my data, and I'm creating a data frame called DG and another one called DL. But I might run my code, and I might not be sure if I have my data in the form of a data frame or not. So it's useful to know sort of what that looks like. So if you just pull up, if you just go to Google and say, like, just type something like, how do I convert a matrix to a data frame in R? You'll see there's lots of help online. When you have a matrix such as this, you're going to always see these kind of square bracketed row and column headings if you just simply were to print it. So if I have a matrix here called mat1 and I printed it, I'm going to see this. I can convert it to a data frame. In this case, they're calling this df2, and they're just with this statement here, as.data.frame. And then this T will transpose the matrix again. So, and that's simply just converting all the rows to columns and the columns to rows. So this is actually very nice. There's not a lot of languages that make transposition as easy as R does. But then if I print this out, you can see that now my headers are quite different. I don't have these square brackets anymore, and I have actual row numbers and things like that. So that's a good way to tell if you're is the data you have, how is R looking at it? Is it looking at it as a matrix or a data frame? Now, if you notice in my R scripts, which I just was showing you, I like to work with data frames whenever possible. So here I have, I always start with read table because you're always bringing data in somehow. So I use read table. I tend to use tab delimited text files. I tend to go back and pull each column independently according to whatever its header name is. This might seem like kind of a waste of effort here. But one thing that this does is it ensures that if I have a column that I know, when I give that column a name, I know I'm working with that column. One of the problems with R, it's very easy to think you're working, say, with column number 3, and really your code's running on column number 2. And that's going to give you wrong answers, and you may not be able to see that or debug that very easily. So if you're taking shortcuts and just bringing in a matrix and maybe analyzing this data G instead of actually creating a data frame that I've called DG, the things might be different here than what I'm assuming, and that can always lead to trouble. So I always just bring in, again, so I have my name of my data that I've brought in, and then and then you use the $sign and the name of whatever the header is on the table, and that will always bring in just that column. And you could print that just to see that that is that column of data. Always a good thing to do. But before I analyze it, I'm going to need more than just one column, so I'm going to rebuild my data frame, and I can actually rearrange my columns here very easily if I wanted to. So all of my scripts have this convention of bringing data in, and it's a little bit verbose, I'll agree, much like me, but hopefully it's a lot clearer as to what's going on. Now, here I'm using my first plot. Again, this is ggplot, and I have an assignment operator here, and you'll notice now that I'm making actually 2 plots, and I'm conducting 2 statistical tests. So if we kind of clear my console here and go ahead and run this, you can now see that I have 2 plots popping up, and these 2 plots are actually on the same PDF. They're on the same page. Wow, that's pretty cool. I haven't seen R do that before. Well, that's because I'm also using the Grid Extra library here, the Grid library. Grid or Grid Extra are what you would import. And then as I'm using, you can read more about this on the on the man pages. But basically what you're going to be doing is I'm asking it to set up sort of a grid layout here. This could be 3x2 or 2x2 or 1x2. In this case, I'm wanting 2 rows and 1 column, so I'm setting them directly above each other. And then I'm putting my plot in each of those positions. So the layout row position and the layout column positions are here. And then I can go ahead and so the command for this from grid is called, the function for this is called push viewport. Then I have to define my viewport, and then here I actually put in the lines of the layout I want on my viewport. So play around with that. Again, it's not a necessity for the course, but it just makes makes R a lot more pleasant to work with when you can set things up like that. Now, let's talk about the ggplot statements here. They're quite a bit longer, so so you can see that I'm doing essentially 2 statistical plots that are known as error bars. Just for the sake of sort of demonstration, let's go ahead and convert that to look like a slightly different layout. See, now I'm putting them side by side the other way. The second one didn't come out because I believe I have to have it reversed as well. There it is. So, very useful thing to do. Now let's look at the ggplot line here. I have my data frame can be my data, or I can simply just specify my data. So actually I've done this two different ways. So for plot number one, the plots are really the same type of method being run, but you can see that ggplot is pretty open. I can give it essentially the table data directly, in this case data G. Or I can actually give it the data frame that I've created, but if I do that I need to specify it as data. And this is always the first argument in ggplot. And then in the second argument that's usually required is some sort of aesthetic mapping. And in this case I need an x value and a y value, and in this case my x values are types, or they're categorical types of variables. And then I have this plus geom box plot, and I'm not really passing any arguments to that, but that's telling me that I want a box plot for my output. Now I have labels that I've actually written on my plot, and I haven't shown that before, but I can actually add plus labs for labels, and then I can give my x or my y. So instead of putting an x and a y, or whatever the name of my data is, whatever the variable name of my data is, I actually want it to actually have a more informative label, so I can write those in that way. Now the rest of this is the very powerful theme command for ggplot. Sorry, now these can get quite complicated and complex, and this is just one example, but I wanted to angle, for instance, my x labels by 15 degrees. So I now have an angle for my text element. And the main way, now again, this is kind of too much to learn and keep in any sane person's head. So, always go online, sort of look up, I want to angle my x values in ggplot. How would I do that? And you'll find someone online will have a way to show you how to do it. I'm also, filling in, using a gray background here that normally wouldn't be there. So I could change that. I could change the color of that background. I could also change the darkness of, gray 10 versus gray 50 versus gray 25. So I can change the level of grayscaling in that plot as well. There's almost no end to the different themes that you can alter. And if you don't have any themes, ggplot will just assign you a theme, so you don't have to worry about it if you don't want to. You only worry about it when you want to change things. This is the beauty of it. So when you're in the normal R plotting functions in R, if you don't specify something, then all you get is a black and white wireframe, which looks bad. But the nice thing about ggplot is it gives you a theme, and it gives you grids and things like that without asking. So it gives you a fairly nice thing, but then you may want to change them so that you have the flexibility of changing them by going back and just adding to this line, and adding to theme. So that's more advanced ggplot. There's a lot more to it as well, but this can give you quite a high level of control. I'm going to show you one more sort of plotting function from another script that I have when we get into sort of showing you how to control R from another coding language, which some of you in the class might be very interested in learning how to do. So, and I'll finish the video kind of showing that. The last thing I want to talk about though here is are these two test statements. So again, you'll notice I'm always using, when I create a plot or I create a test, I'm using the R's assignment operator, or this back arrow, to assign whatever that test is. I could just, I could leave that out and just print it, but it's much more straightforward logic to actually give it an object, create an object that is the result of that test, and then I can actually pull out numbers or analyze those independently if I wanted to by working more code on this particular object. So if I just wanted one of the values, I didn't want everything that's coming out when I do that. Typically this prints out to your console, but if I were to want to send it somewhere else, for instance, I think I've showed you this before, there's a very valuable sort of function called sync, and if I were to sync here and then I call it, my text file.txt, if I were to put a sync statement here and then afterwards I closed my sync. So you have to sort of open your sync and then close your sync, and what that's going to do is anything between these two sync statements is going to go to this text file and print out there instead of to my console. So I could have it go to my console and then I could duplicate my code and send it to a file that I could save and open up later. Having everything on your console, especially the statistical results that you want to keep the results for, you may not want everything going to your console. You might want it to your console to read it, but then you don't want to have to write it down manually. So syncing things, or you can also use the write function and write things out to text files, but I find that sync is very useful because just however it looks on the console, that's what it's going to look like on this text file. It's going to give the same results there. So don't forget about that. That's a very one of the nice and relatively unknown tricks you can do in R. Now, I can look at my output here. I've done essentially a one-way ANOVA, which is looking for statistical differences between these groups. And I've also done sort of pairwise t-tests as well. Now, I want to point out something about the arguments of these two tests. So I have a one-way ANOVA here with a p-value. It's highly significant. So it does look like there's statistically valid differences between these groups. And then I've done a whole bunch of sort of pairwise t-tests. I'm getting p-values for all of those. Be careful not to do any p-hacking. If I were to, I should correct these using a p-value adjustment method, and this actually does it automatically for me. It gives me a Bonferroni adjustment. So these p-values are adjusted for the fact that I'm running this t-test over and over again, more than once. That's important. Now, let's talk about arguments to functions here. You're going to notice, maybe if you've sort of looked more carefully, you're going to notice the arguments for these tests are different. This one has essentially my y values and then my categories or my grouping values, and then in between there's this little squiggly line right here. What is that? Well, that's indicative that this argument for this test is a formula. It wants a formula, and it wants on the left side of that formula essentially the y values or the dependent variable, and it wants the x values or the independent variables of the statistics on this side. So if you go to the one-way test man pages, so go to the R documentation website and look at one-way test, you can see that the usage here for one-way test is that it wants a formula as the first argument. It doesn't give you any other options. It wants a formula, and then it wants your data. Okay? So that data can be optional. It can be a matrix or a data frame. But if I just gave it data and I didn't give it this formula, it would throw an error. Okay, it wants some sort of a description of, and a lot of our functions are like that. Some of them want them, some of them don't. If I go over to pairwise t-test, you can see that it just wants my my response vector, and then it wants my grouping vector or factor. And it actually doesn't want a data frame. It doesn't want a data. So again, that could be problematic if you always go back and check these arguments. If you just sort of assume that I can give data, just my data frame, to this pairwise t-test function and expect it to work, it might throw errors, and it's not your fault. It's just because whoever wrote it this way made it rather constrictive in terms of its arguments. But you're going to see this convention a lot: a formula followed by the data, followed by other things. These are not all required arguments. Obviously, my one-way test ran with just with just my formula stated, and the data was implied in my formula, so it actually ran well just with that. Whereas my t-test function, let's go back to RStudio and look at that again. Required at least 3 arguments. It required my my vector, my data vector, my grouping vector, and then those arguments are always separated by commas, and then it required my method of adjustment here. And then the rest of the arguments that were mentioned on there, all of these things, I could do a paired t-test. I could specify that true or false. A lot of times these are just specified for you if you don't say one way or the other. So you go back and read this more carefully and figure out what sorts of assumptions it's giving you if you're not going to specify them in the arguments themselves. So just another tip, always come back to look at the arguments required. And the best website to sort of show these arguments to you is the R documentation page, because I don't need a tutorial. I don't need to know what ANOVA is. I don't need all this other background. I just want to make sure my arguments. So the arguments, you always have usage, an example, and then you have the arguments listed out and what they are. Very useful, very handy for R when you're getting started. Okay, I think I've covered everything except what if I want to run R from another program. Now this is maybe some of you in the class coming from computing science might be very interested in knowing how to do this. If you're just getting started with R and it's your first language, no worries here. Don't worry about it. But it's nice to know what's possible with it. I'll talk first about Python. Python is a language that a lot of people these days start with. It's a language that's been around a long time. It's been around. It was a language available to me when I was young. So it's not, by any means a new language, but it has a lot of young development and a lot of young programmers working with it, more than some of the other languages. Doesn't make it the best language. In a lot of ways, it's restrictive in my opinion. But because the development is happening in Python, it has the ability to do things that you wouldn't find in maybe other languages. If you ever wanted, though, to run R, now, there are lots of data science packages you can run right out of Python, and you might ask, why do I even need R? That's valid. I mean, most data scientists actually use both R and Python and use them almost interchangeably. So it's good to know how to go from one to the other. If you're in Python, I would recommend with these, Python and Perl is what I'm going to show you today. These are general purpose scripting languages. R was really never general purpose language. It was always designed essentially for mathematics and statistics. So you really don't want to use it for anyone else. It's best to use it as a back end, almost as a library. It's a whole bunch of statistical packages and things that you might want to use. But you might want to use them from a different language, especially if you're writing a complex scientific pipeline or something like that. So typically when you want to run something from another language, you're going to do what's called a system call. System calls are in a lot of other languages, JavaScript or Perl, you're just using the word system and then curly braces, and then you type whatever you would be typing on your terminal to actually run that script. So in the case of Python, though, more recently, I guess system calls were problematic for several reasons, especially when going over from Python version 2 to 3. So now the main convention that they tell you to do is to use the subprocess module. So this is it's like a package in Python. Packages are called modules. You would import the module and then run a subprocess. So something like this here is a good example of what this would look like in Python. So Python doesn't have or it doesn't. It is white space sensitive and it's indent sensitive. So it's a little more restrictive, but it makes the language a lot more readable. Code blocks always start with a colon here, so this is a with loop, and then within that loop, there's a process being called, and then we're waiting for that process to finish essentially here. So the script file name. So I'm importing subprocess. My output can be, whatever I want to name it. My input script is the .r script here. So I have a script called, in this case, hierarchical clustering .r. And then whatever parameters, I might need a data file that's associated with that R script that it needs to read, and I might, have my results coming out from, that sync function that I showed you earlier. So these would all be arguments to this subprocess. So when I run the process, subprocess.popen, and then here I'm running the R script function. My second argument is my file name, and then my two parameters here. So relatively straightforward in Python. I'm actually going to demonstrate something a little more complicated, but actually very, very useful to do in Perl. Now, Perl is probably the most flexible language. It's one of the hardest languages to read, but it's one of the easiest languages to write because it has almost no conventions in style. It doesn't recognize white space at all, so or indents at all. You can write all of your code on a single line if you want. You can go down the page. You can go both left. You can go right across the page and down at the same, at almost the same time. So Perl coding is not for the faint of heart, I suppose, and was more popular with my generation than it is now. But it's still actually, if it's a great language for just getting something one and done, and it's a great language for controlling other things and controlling a complicated pipeline. It's almost like a bash script. But the nice thing about Perl is it's a type of bash scripting that can run on any platform. It can run on Mac and on Windows and on Linux, unlike Bash, which only runs on Linux. And it has all of the early functions of scripting from back in the 1990s when it was very popular. It caught a second wave of popularity in bioinformatics, and if you're going to become a bioinformatics major or work, you're probably going to see lots of legacy Perl code, so it's probably worth learning just for that sake alone. It could make you very valuable, actually, a highly paid employee if you know how to program in a language that people don't really use anymore, especially if there's a lot of important legacy code laying around. So this project here that I've talked about is from my lab. We use... this has been written up in Biophysical Journal, and it's basically a pipeline for analyzing how proteins wiggle and jiggle and how that might affect the way that they function and how you can compare those motions in simulations over time. I'm not going to talk really sort of about the mathematics behind it, but it's been an ongoing project of ours that involves the languages. A lot of it's in R, a lot of it's in Perl, and a lot of it's in Python. So we're using those languages almost equally on the project. So it's important to be able to run things from one to the other. So let me sort of show you an example of what this might look like. So let's get out of our studio, and now I want to go back and look at my editor here. So in my editor, I have a Perl script, and this is a Perl script that is controlling R. It's actually running statistics. I'm doing a lot of statistics. I'm doing plotting. I'm doing Kolmogorov-Smirnov tests. I'm looping this and doing this amino acid by amino acid across the whole protein. So it's quite a process. It's not something I would want to code strictly in one language like R, although I probably could. I can handle sort of motions, and the one thing that's nice about Perl as a language is it's very good for handling strings of text. And so if I'm actually walking down a protein where I have specified the protein sequence using letters of text, Perl is a much more natural language for manipulating and working in windows of text rather than mathematics or things like that. It's actually very poor with mathematics. I would never want to program a statistical test in Perl. But Perl and Perl and R, and more recently Python and R, are often combined, because that in bioinformatics, that's what we're doing. We often have DNA sequence or letter text as our input, and then we need to do mathematical analysis on it. And there is no one language that's great for all of that. So a lot of us over the years have learned to use Perl on the front end and R on the back end. And the way we do this is often through something known as a pipe. And I'm going to demonstrate that right now. So let me pull up my my other terminal here. So in this terminal, I'm actually opened up to where my Perl script is, and although you may not have ever seen Perl before, it's certainly not the most readable language. But I'll just go ahead and kind of show you the layout of this. Everything above this, these lines here called subroutines. Everything above this, which is called the main loop, is actually just setting up a graphical interface. And so when I go here and I open up my graphical interface, it actually has, oops, it's covered up with my picture. There it is. So it's a little graphical interface here that's controlling my statistical tests. So I can actually change my level of significance by using the slider bar. I can use multiple test correction. I can use Bonferroni or another method here, or I can use none at all. And then I can select different chains. If I had a protein that had 5 chains in it, it would give me a list of those chains, and I could select the analysis where I wanted to put it on the protein. The first little button here sort of just creates a control file. And now what you're going to see here, if we were to walk down this Perl script a little deeper, so this first subroutine is what created my control file. But if we go further down, you're going to see that I have a subroutine here that is actually controlling the statistics. And that's this subroutine called stats right here. And it's actually the bulk of the entire script. And if you go into this, you're going to see many places where I have print, R input, and then I have something here that looks quite a bit like what I might do in R. So here you can see this is very similar to what I was showing you in my R scripts. I'm actually using a read table function. I'm bringing in the data. I'm pulling the headers off of that data table, and I'm creating a data frame right here. And then I'm running a ks.tests function in R. So basically what this is actually doing, this print R input is something we call a file handle. And what it's doing is it's opened up a file handle much the same way that I would open up a file to either read or write to it. And in Perl, if I was going to read or write to it, I would actually use, if I was going to write to it, I would use a forward angle, and if I was going to read from it, I would use a back angle like that. But this other thing is actually called a pipe. And what it does is it basically means anytime I print, so my file handle is here, and anytime I print to whatever that file handle is called, it will just do whatever I would type, like on my console, my R console. So the first thing I might type is get me a ggplot library. And the next thing I might type is read my table in. So this will just automate all of my finger strokes that I would use in R. But I'm controlling it from a different language. I'm controlling it from a script in Perl. So it's very handy. And when would I might want to do this? Well, if I was just going to do it once, run through this once and make one plot, well, I might as well just do that in R. But in this case, I'm actually running amino acid by amino acid and doing an analysis that needs to run that KS test on every single amino acid. And then when it's done, you're going to see I'm opening up another pipe, and now I'm creating a much more complicated graph here that's going to have actually 3 different plots plotted to it. So let me just go ahead and sort of show you what this, what this would look like. So back on my console here, I'm ready to go ahead and start my analysis. And now you're going to see on my console it's actually recreating my finger strokes very rapidly. It's not too pretty. It's always, kind of scrolling across the terminal. But it's using a Perl script to control R, in my terminal right here. So I'm not using RStudio. These are all terminal commands. And once it gets to the end of this protein, which I think is about 70 amino acids long, we'll wait a minute here. Then it will kick in here and it'll actually pop this R plot to my screen. Now, one thing you need to remember, if you are running R from the terminal and you're not using RStudio, then where does your plot go? Well, it always goes to a PDF file that's created called R plots. And so what I would be doing, once I'm creating that plot, is I'll generally copy it with a slightly different name, and then I'm gonna. So I have these copy functions here where I'm actually changing its name and sort of printing things out, and then here it comes. It's going to pop a script. So here I have a 3-panel R plot. It's nicely controlled. It's got I've been using, again, this is a ggplot, so it gives me the exact colors I want for all my amino acids here. I can pick different R colored palettes and do that sort of thing. Basically, this is looked at 2 molecular dynamic simulations on a protein and then a copy of the same protein at the same temperature, and it's just telling me if there's significant changes between the dynamics or the motions on those amino acids in that simulation by using that KS test. And it's coming back here and looking at, all of these are essentially not significant. So these are not, you can see there's almost no difference in the profiles of the fluctuations across this protein chain, and when I get down here, none of those are significantly different. So that's what this output sort of shows. And then I'm using the Perl script to actually pop this up in my pipeline. So it's actually using in the PDF reader in Linux is a program called events. So it's actually popping events up and opening up the file that was created by R. So that's a much more fancy way to kind of control things. And I just wanted to show that, you can write in these languages like Perl and Python, you can write your own graphical interfaces to do your own statistics, your own custom things. And then you can, run those, and you can use R as a back end to do your analysis. I don't want to recreate all of the technology that R is able to bring, but I don't always want to do everything within RStudio. You know, for simple tests and things like that, doing analyses, RStudio is great. But a lot of times for a much more complicated scientific pipeline that's doing very specific analyses, maybe across lots of DNA sequences or across lots of protein amino acids, then I'm going to want more flexibility, and that's what Perl and Python languages bring to us. Again, this is above the level of class. Don't freak out. Don't worry about, you know, I'm not going to require that you do anything in Python or Perl. But if any of you are interested in wanting to see more of this and you want to try it out, do talk to me in class, and we can have some fun and play around with it. Okay, thank you very much.